discuss the fundamentals of the Laplace transforms, okay, applications to network analysis, and we have discussed also the Laplace transform of some basic functions, okay, and today we should discuss about the analysis of circuits, analysis of circuits using Laplace transform technique. Okay, for this, you will have to know the concept of step input response, step input response for RL circuit, RC circuit, and RLC circuit, and also you will have to know the responses for different types of inputs, that is standard inputs. The standard inputs are step input, ramp input, and parabolic input, and impulse responses. So those things you can study. So here what we shall do, we shall limit ourselves to the transient responses or responses due to the standard inputs such as step input only, so that you can also concentrate on different types of inputs. Okay, so for that we should know the fundamentals of how the inductor behaves during the switching condition, and how the capacitor behaves during the switching condition. The transient transient analysis knowledge is very important. So what we have studied in the third chapter, transient responses, those things you require. Okay, so what we shall do, we shall take up about so one simple circuit, and when we do the transient analysis or step input response, step input response for RL circuit. So you can just concentrate on the procedure. You can the same will be applicable for RC circuit and RLC circuit. Okay, so let us have a DC excitation, not the AC excitation. So this is a DC excitation, and you have got a circuit like this, R and L here. So R and L, and you have got a switch like this, which is getting closed at t is equal to 0, and this is V. So you can have a current I of t like this. So if you apply KVL here, so you get R into I of t plus L into d I of t by dt, that is equal to what? V. Okay. So what is that we have assumed here? Step input response. Step input response. That is nothing but unit response. Unit step input response. So V is equal to what? Step function. Is a step function. Step function is like this. This is a step function. So T, and this is the output. So it will be non-zero for all t greater than or equal to 0. That is the step input. And so what is a Laplace transform of step input? Is nothing but 1 by s, or it is nothing but v by s. In this case, it is v by s. So what we have to do, we have to apply the Laplace transform here. So it is r into I of s plus L into s for the first differential, and this I of s, and you have to use the initial conditions of the inductor. So it is minus I of 0 plus, that is equal to V by S. So this is what the expression, and I of 0 is assuming that 0 initial conditions and making I of 0 plus as 0, then you can simplify for I of s. I will just rewrite the same equation on the next side. So it is nothing but R into I of s plus L into S into I of s minus I of 0 minus or 0 plus, because the current through the inductor will not change instantaneously. So this is what the initial conditions. Okay, assuming that initial conditions are absent, so you get R into I of S plus S into L into I of S is equal to V by of S. Okay, so simplify for I of S is equal to V by S into R plus SL. So this is the expression for I of S. Okay, so what is that you can do? You have to bring it to the standard format in terms of so that you can apply the Laplace inverse. Okay, so using partial fractions, you have to simplify it. I'll just rewrite this one in the next equation, next sentence. So it is, I write the equation again for simplicity's sake. I of s is equal to V by S into R plus SL. So taking because you have to make the coefficient of S as 1. So you have to make coefficient of S as 1. What is that you can do? Just take L common factor in the denominator. So it is V by S into L into R by L plus S. Okay, or it is V by L by S into S plus R by L. So this is as good as nothing but S into S plus A, like that. So I'm keeping it in standard form, S by S into S plus A. So V by L happens to be the constants. So split up using the partial fraction method. It is nothing but K1 by S plus K2 by S plus R by L. Okay, and this is the expression for I of S. Then you can solve for the K1 and K2 using initial conditions. Then you can take the uh, Laplace, means you can take the Laplace inverse later. So if you solve for K1, you will get it as V by R. This is at S is equal to 0. And you can solve for K2, this is equal to minus V by R. This is when S is equal to minus R by L. Because the roots of the equations are 0 and minus R by L. Okay. So now just substitute those things in the standard expression. The first expression, I of S is equal to V by R into S, okay, minus V by R into S plus R by L. So this is what the expression for you. And if you take the Laplace inverse, you will get V by R into 1 minus e power minus R by L into t. So this is the expression for current or the response using Laplace transform method. So I have used Laplace transform method. So you can repeat the same for RC network, and you can also repeat the same for RLC network, network. So, and I am restricting myself to the unit step function here. I'm not doing it for the other step, other inputs such as ramp input as well as pulse input. Okay, I'm also restricting myself to myself to the DC analysis and not the AC analysis. So the AC analysis remains same, but you will have the different expressions. Okay, so what we have done in the initial conditions chapter. Okay, so what is that I am doing here? I'm just explaining the responses, using Laplace transform. What is that I'm doing it here? I'm restricting myself to DC analysis. I'm restricting myself to step input only. So you can also extend this to AC transients, and you can also extend this to different types of input such as ramp input, parabolic input, and also the pulse input. So these three inputs you can extend it analysis. So I'm restricting myself to DC input and step input. And I have explained for a series RL circuit, you can extend it for a series RC circuit and RLC circuit. Okay, so this is what the application of Laplace transforms for getting a response in a DC, RC, and RL network. Okay, so now, so let us now apply the Laplace transform to the circuit analysis. Okay, so let us take one example here, um, and we can conclude. Okay, so application of Laplace transforms. Application of Laplace transform to circuit analysis. How you have to how you can directly apply the Laplace transforms to circuit analysis. So, for example, you have got a series RLC circuit, okay, and you have got a voltage source like this, and the current is flowing like this, I of t, and this is V of t, R, L, and C here. Okay, so applying KVL here, so we will get R into I of t plus L into di by dt plus 1 by C into 0 to t I of t dt plus, so it is Vc of 0. Vc of 0 is equal to V of t. So Vc of 0 is what the initial conditions. Initial conditions you have to consider with respect to the capacitor. Okay, so you can take the Laplace transform. You can take the Laplace transform. I'll just take this the next slide. So take the Laplace transform. So R into I of s plus s into, it is L into, okay, s into I of s minus I of 0 minus plus I of s by C plus Vc of 0 by s is equal to V of s. So I'm not taking V as constant, it is a variable input, so it is V of s. V of s can be anything. V of s can be unit step, it can be parabolic, it can be ramp, it can be impulse input. So you can solve for I of s here as before. So you get V of s plus L into I of 0 minus Vc of 0 by s divided by R plus S into L plus 1 by Cs. Okay. So how you can represent this equation in network analysis? So you can represent the initial conditions of inductor and capacitor like this. For example, in this example, you have got a circuit like this. So you have to represent the circuit in Laplace transform RLMC like this P of t. So like this you can do it. So this is R and this is, you write an inductor and you have to represent its initial condition by some voltage, that is voltage is L into I of 0 plus, L into I of 0 plus, L into I of 0 plus or 0 minus. So this together is what the initial conditions representation of inductor. And coming back to the capacitor branch, so write the capacitor as it is. So it is, and this inductor you had write it as S into L, okay? And this is what 1 by CS, and you have to represent the initial condition of capacitor like this in terms of VC of 0 by S, okay? And complete the circuit like this, V of T. Okay, this is one part and this is another part. This represents the inductor part and this represents the capacitor part. Okay, so that is how you can include the Laplace transforms application to circuit analysis. That means you are writing the initial conditions in terms of series voltage sources L into I of 0 plus and VC of 0 by S. Okay, so and also what happens to the final, that means this is the numerator V of S plus L into I of 0 minus and minus VC of 0 plus is nothing but the uh, voltage of the circuit and divided by the impedance. So you can also write the total impedance as Z. This Z is equal to R plus S into L plus 1 by SC. This is the total impedance of the network. So what happens here in the previous case? So it is I of S divided by is equal to what? Voltage by impedance. So impedance is represented like this: R plus SL plus 1 by SC. That's all. Okay. So one second. Okay. So this is I of S is equal to V of S plus L into I of 0 minus VC of 0 by S. The numerator is nothing but the voltage function, and denominator is nothing but the impedance function. So you can take this as a reference. Okay. So what happens here? You can just check out how to represent that voltages across the inductor and voltage across the capacitors. Okay, so now let us understand the behavior of each element uh, in terms of the passive element, that is R and C. So first we should discuss about the capacitive element, how to represent in Laplace network. Time domain network is different, Laplace network is different. The capacitor voltage is given by Vc of t is equal to Vc of 0 plus 1 by c is equal to, once again, okay, so 1 by c is equal to 0 into t ic of t dt, ic of t dt. So it is ic of t is equal to c times into dvc of by dt. So taking Laplace transform, so you can write vc of s is equal to vc of 0 by s plus ic of s by uh, c into s. Okay, so this is the equation 3. So this is the equation, very important equation. So this equation, that means whenever you get capacitance, whenever you get capacitance in the network, you have to replace that capacitance. You have to replace, this is a time domain network, and you have to replace that capacitance by 1 by SC in the network. Okay, so this is what important. This is what important thing in the Laplace. Okay, so and also if you simplify for the current, if you simplify for the current, or if you write the equivalent circuit, the capacitance here in time domain network is will be like this. In Laplace network, it will be like this. Okay, so this is 1 by SC, and this is VC of 0 by S. Okay, this is the current IC of S. This is flowing, and this total is what VC of S. Okay, so you can also source transform it. You can also source transform it. How to source transform it, you already know. So what you do, source transform this one, you get the branch here, and you get a current source like this. Okay, so this is VC of S, and this is 1 by SC as it is, and this is nothing but C into VC of 0. Okay, how do you get this one? So it is nothing but VC of 0 by S divided by 1 by SC. S and S cancels, so C into VC of 0. This is nothing but source transform. So you can either write the current, the capacitor in terms of voltage source, or you can write capacitor in terms of the current source. That's all. Okay, so what is that? You have to understand, whenever you find capacitor, it has to be replaced by Laplace term 1 by SC. Okay, yes, next come back to the behavior of uh, the inductance. Inductive element, let us discuss. So how the inductive element behaves, very similar fashion. So it is VL of t is equal to L into di of t by dt. So it is IL of t is equal to IL of 0 plus 1 by L integral 0 to t VL of t dt. Okay, so taking Laplace transform with VL of S is equal to S into L into IL of S minus L into IL of 0 minus. Okay, this is as good as writing inductor. Okay, inductor like this. So this is L, and this is VL of t, and it is IL of t here, IL of t here. This will be in Laplace domain. It will be SL, and in series with the voltage minus to plus, and this is what VL of t as it is. So it is L into IL of 0 minus, and this is IL of t. Okay, so this you can also convert this into current source. It's also possible. So what is that you have to understand here. So inductor here in time domain will be replaced by S into L. That is in series with the voltage source of value L into IL of 0 minus. Okay, this is what very important. Okay, so let us take an example and you can easily apply it directly. So for example, you got a network like this having R, L, and C. Convert this into Laplace. Convert this into Laplace domain I of t. Okay. So what is that you will do? You will just take this current inductance branch, replace L by SL, add a voltage source in series. That is nothing but L into I of 0 minus. And next, this is nothing but capacitor branch. It has to be replaced by 1 by SC. And that has to be replaced by voltage source. It is VC of 0 by S. That's all. So apply the same voltage. The same voltage is V by S. Understand? So L branch has been replaced by this branch. Okay. And this branch has been replaced by this branch. Okay. So whole of L is replaced by this one and this one. That's all. Okay. So now you apply KCL. Sorry, if you apply KVL, you will get the answer. Apply KVL here in this Laplace transform. Is R into I of S plus S into L into I of S minus L into I of 0 minus plus I of S by SC and plus VC of 0 by S is equal to V of S. This is what the KVL for the network. Okay. If it is clear for you, you can type 0 in the chat box. Yes. Now you can apply the same concept to the meshed network. You can apply the same concept to the meshed network, plus minus. This C1, this is C2, R1, this is R2, and V1 of T, and V2 of T, and this is L, I2, I1, and this is I3. Okay. So you just have to write the Laplace transform network. Laplace transform network like this. So you have to replace that inductor. Replace inductor by SL and current. Sorry, voltage source minus plus L into IL of 0 minus, and you will get 1 minus V2 of S. Okay, that's the first thing, and this is R1 as it is, and this is R2 as it is, and capacitance will be replaced by 1 by SC1, and voltage source plus minus, it will be VC of 1 of 0 by S, and one more capacitance 1 by SC2, and voltage source VC of 2 of 0 by S, and here it is plus minus V1 of S. That's all. Now you can just simply apply the KVL as you have done in mesh analysis. That suffices for the problem. That's all. Clear? So if you have understood this problem, then type 0 on the chat box. Let us take one more example, and then we can solve for it. Yeah, got a network like this: capacitor, resistor, 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 plus minus. Is a unit step function u naught of t, and I of t 1. It is 1, 3, and 2, and it is 1. Okay, so this V2 of t is equal to 2 VC of t. Okay, applying Laplace transforms, unit step function it will be replaced by 1 by S, resistance as it is, okay, and capacitance 1 by SC. S into 1 is 1, yeah, that is S, and voltage source plus minus, it is VC of 0 minus by S, or 0 by S, and this is network, and this 3, 1, 2, and this 2 VC of S, 2 VC of S. That's all. Okay, this is a transform network. Okay, so if you have understood this problem, please type 0 in the chat box. Yes. So I'm not going on to the next step. So I'm just traveling around, writing the transform network for a given time domain network. That's all. Solving and all, I'll just leave it to you. Okay, it is as good as applying partial fractions method. Okay, I'll take one more example and then try to explain that concept. So you will get like this. Henry, IL of 0 is equal to 1 amperes. Okay. So the values are given for you. Now you have to solve for the current in the inductor. You have to solve for current in the inductor using mesh analysis. It is IN of t. So write the transform network, and the voltage is 2 U naught of t. It is, you get the transform network 2 by S. It is 1. It is S into L. 0.5 S, and it is 1 by S. It is 2 by S, and it is 0.5 into 1. 0.5 into 1. So this is I1 of S and I2 of S. So applying KVL on the first mesh, let us solve for this one. So applying KVL onto the mesh, first mesh. So it is you will get it as 2 into I1 of S. This is 2 I1 of S. Okay, and plus I1 of S minus IL of S, that is I2 of S. Okay, divided by S plus 2 by S minus 2 by S, that is equal to 0. So I just applied KVL in the first mesh here. Okay, so it is nothing but I1 and this is nothing but I2. So I applied KVL here. So I1 of S minus IL of S, okay, divided by S. S is common here. S is common here, and 2 by S is the drop here, and minus 2 by S again here. This one is equal to 0. Similarly, on the left hand side, on the right hand side, if you apply, so you get minus 1 by S into I1 of S plus 1 plus 0.5 S plus 1 by S into I2 of S is equal to 2 by S plus 0.5. So this is the second equation. First equation and second equation. Very simple KVL. So I'm not exaggerating here. Okay. And next part, you have to solve for I1 of S and I2 of S. So I1 of S and I2 of S you have to solve, and you will get a matrix like this. You'll get a matrix like this. Okay. So it is I1 of S and I2 of S. Listing of the coefficients, that's all. Coefficients here, and this is the constants here. Now, using that equation 1 and 2, you can just mark the coefficients. You'll get 2 plus 1 by S here, and minus 1 by S here, minus 1 by S here, and 1 plus S by 2 plus 1 by S here, 0 here, and 2 by S plus 1 by 2 here. If you multiply these two, you get the same two equations. Okay. Then you can simplify it using partial fractions method. It's a very big problem. As it is a 2 cross 2 matrix, it is a very big problem. You will have another 8 to 10 equations. So it is a very tedious process to solve by hand. So you cannot expect this to be solved in given time. Okay, so you can just study up to writing the transformed network and writing the equations thereon, and that's all. That is sufficient from this concept point of view. Okay, if it is clear for you, please type 0 in the chat box. Okay, okay. I'll just stop at this point. Uh, this completes the Laplace domain, Laplace analysis for circuit analysis. Okay, so I have just done only the fundamentals part. I have skipped the final value theorem, initial value theorem, all those things, and the fundamentals derivation of the fundamental conversions. Okay, those things I have skipped. It is not required. Just you have to know those fundamentals derivations. That is Laplace transforms of standard functions of time. Okay, Laplace transform of sine function, Laplace transform of cosine function, Laplace transform of sine hyperbolic, Laplace transform of cos hyperbolic, Laplace transform of e power minus at. Like that, you can just remember. Okay, you might have studied these things in the mathematics part. Okay, just stop at this point. Tomorrow we shall solve some more problems on these things.